So welcome to this video, to this lecture. And in this video, I want to talk particularly on train and test. I want to talk about training and testing. Yes. Now, what is training and test? And because you usually hear train and test split, we usually hear about cross validation, and I would like to talk about this in this video. So let's jump into it. So let's say we're given some data set, right? And the data set basically that we're given is, let's take the case of a trading example. Let's say we do have a trading case here. So let me do this. We have a trading case here, and we're given the features that we have here. We do have the features here, and then you have the target variable basically. Now, the features are, let's say we're given the type of candle, so whether the market went up or down. Say we're given, as you can see here, x2, whether, for example, the close price minus the moving average, and the other data set could be also the feature could be the daily return, for example, for a particular stock or for a particular asset class, right? So we do have the x variables and we have the y variables. The x variables are called the features, the y variable is a target variable. And let's assume for a minute that the data set is a time series. So basically we go from old to recent, right? From up to down. All right. So how would we split this data? So let's say we do have this data and we want to train a machine learning model, and hopefully the machine learning model would have learned representation between the input, between the features and the target variable, and the model will be good enough to predict, to have good predictions for future data sets, right? And then here, the target variable is we are trying to predict whether the candle, the next day candle, is going to be a bull candle or a bear candle. In other words, we are trying to predict the price direction. So let's say, given this data set here, can we predict whether tomorrow the price is going to go up or the price is going to go down? This is what we're trying to do here. Okay, so if we have this data set, somebody might say, okay, so I need to use the entire training set, right? I need to use all this data to train my model, right? So that at least I do have all my training sets. I train my model is robust enough. And if I give my model any data that it has not seen, I'm much confident that the model is going to be predicting good. Who thinks that is this is a right approach to do it? Not me. And you might see that many people do not agree with that, because if we do this, there is no way for us to know if our model is good or not, right? So by training our model on the whole data set, there's no way for us to validate whether our model is good, because we just go, that would be like a gamble, right? So you train a model on all the training set, and you go and use a model on data that you've not seen, and that is called, let me write it here, it's called a gamble, a really big gamble, right? Let me delete this like quickly. So we're not here to gamble. What we're trying to do here basically is to say, okay, what if we actually train the model on a majority of the training data and then test it or evaluate it on only a tiny portion, right? Tiny portion here. This one here will be the test set. Well, we can actually do that. We can actually do to, train a model, and the pros of this is that the train set, the train data is a lot. The cons is obviously the test is much less. So the confidence, so also is the confidence in the model, right? So the confidence is going to be eroding because we've only tested the model. We're only going to test the model in a small data set. We're not sure whether the model has actually learned valuable information, because new data might come and then the model might actually be predicting crap. So what can we do? So what we can do, let me delete all this, for example. Let me go back. What we can do, right? Okay, oh, I went too far. Okay, so what we can do, we can say, okay, let's at least have about 70% or even 60% the trend set. So let's say 70% in the trend set and 30% is going to be test set. So let's say we do have the trend set here, and here in green I'm going to put here the test set. Okay, so let's say this is our example here. We do have a trend set and a test set. Now at least you can see that what we're trying to do here, given that if we have a lot of data, or even decent amount of data, at least we could have sufficient amount of data for the trend set, and we have at least decent data for the test set. So obviously we're not going to have full confidence because the test set is not a lot, but what we can hope for is that the distribution of the data in the test set is similar to the one in the trend set, right? And that can be a homework for us, because we want as much as possible the trend set to have similar feature in the train set. Because say if your model learns something here that is not here, then you shooting yourself in the foot, because obviously your model is going to be disadvantaged. It hasn't learned what it's supposed to learn. So the separation of the trend set and the test set really is an important task to carry out, particularly in this sort of like trading problem, or this sort of time series problem. So then what happened next? So next what we do is we do the following. We say, okay, we send this data to the algorithm, and then we use this data to train the machine learning model, and then hopefully the machine learning model now is trained. And then what we do next is to send this data set here, right? So we send the features of the test set to the machine learning model. The machine learning model is going to now output some Y prediction. And what we do now, we say, okay, can we compare these two? Is this data, can we compare it to this data, right? If we compare the prediction for the Y test versus, if we compare the Y test versus the prediction, are the data similar? Are the predictions about the same? And that is what we are trying to achieve. And ideally you want to have a higher percentage than 50 in the case we do have a binary case, because here it is a binary in the case of binary class. Why? Because we're talking about it's either bull or a bear candle, right? It's either a bull or a bear candle. So we're in the case of a binary case here, and this is pretty much straightforward because you can either have in percentage, so you can compare the percentages for accuracy, and ideally we want to have we want to be above, we want to be above 50%, way more than 50%. So anything around the 60% or so would be good, would be really good, right? And this is what we've got here. So in for trading now, you might say, but why not actually use why not actually use a smaller trend set, right, and then test it on a larger test set? But the problem is that if you do that, let me write it here, if the trend is small, I think it's not good for us, because the problem is that the model learning is not optimal, right? We don't give a chance for the model to learn properly. All right, so it's kind of like a balance, right? It's like a balance. Now, there's something that I want to talk about also is that sometimes other people do something they call cross validation. Cross validation, which is a way, for example, sometimes to determine the performance of different models, right? And consolidation naturally goes like this. I can probably touch upon it quickly, right? So what you can do, let me do this, for example. All right. So let's say for consolidation, what you can do, you can say, okay, you know what, I'm going to train the data on 60% 66% of the data and test it. No, wait. Train it on 66% and test it on some other 30%. Then you get the matrix here. Let me write it here. So then you get the matrix, and then you come and say, okay, you know, I'm gonna move forward for the next chunk, and then I'm going to train the model on this and test it on this. Then you can say, okay, I'm gonna go next and train the model on this and test it on this. And then what you can try to do, somebody could say, okay, I'm gonna average the matrix out. And then average those to estimate what the true metric is, right? But for this particular one, basically, it really depends. So you would do that basically if you would want to compare a different algorithm, for example. So you've done that for different machine learning algorithms. So you can try the SVM, for example, random forest, simple decision trees, I don't know, logistic regression, for example, and then try those, and even neural networks, and then try those and see which one has got the best metrics and stuff. But for trading purpose, I think what is interesting is that if I can do this and I do have the model that performs good here, then I can actually somehow rely on the predictions for unseen data, right? And let me give you an example of how we can do this. So let me go quickly. I will delete all this, right? And then I have some plot here. So let's look at this, for example. All right. So let's say we have this data set, which is crude oil data, and then we want to use this data, train our machine learning algorithm, and then test it on data. So let's say if data goes from 2019 to August 2019. So January 2019, January to August 2019. Now you can come and say, because usually for trading cases, the data is really chronological, so it goes in a really good time series order. You don't want to randomly kind of like take random data, right, and then use it for training purpose and stuff. So what we can do here, we can say, okay, you know what, we are going to take part of this data set to be our train set, and then we will take this one here to be the test set. Now you can obviously see here there's a clear problem, because you might realize that, for example, what is going on here, right? This market that is going up in the up direction, here is going downwards. So the problem here is that a model, this particular model is good. It's gonna be good, right? This model here is gonna be good in bull market. But this particular is gonna be good in bull market. Now, if you test it in the bear market, it's gonna terribly underperform, right? it's gonna terribly underperform because this is not a bull market, right? It is not a bull market, sorry, but it is a bear market. So this model here is gonna terribly underperform. So you can see that if you would want to train a model on crude oil like that, you also might want to take all the data. You can see it looks like, if I look at this moving average, it looks like the data from 2018 was in the bear market, because all this here going in this direction is bear market. And you can see that the price seems to go down here, the moving average is also go down. So you might say, okay, maybe I want to use the 2018 data as well to train my model, so that you do have a bear market, so that your model is trained at least on a bear market and on a bull market, and then you can come in now and test it on a bear market. Think about, you see, right? So these things are important consideration, because that's where the train and test split is important, and then one has to think about it, because you can just go and say, I'm going to divide the data into 50-50 or 60-40 or 70-30%, because you need to make sure that you give a chance to the models to learn features and representation and characteristic and things, market behavior or behavior in the data that is most likely gonna occur and appear in the future or in unseen data. Right, so this is really really important, and something that I wanted to highlight here. So this is the end of this lecture. It's just like a quick brief overview of like really important consideration, particularly for cases in trading and in general in training tests. All right guys, thank you very much, and I see you next time.